Hiya! So in this video, we're going to talk about consecutive odds ratios. So what this basically means is we're actually going to look at the binomial distribution in terms of odds rather than in terms of probabilities. So if you remember back in the first week, basically we were talking about odds. So like this was things like if you're doing like horse races, for example, this is very frequent in gambling where you have like a 2 to 3 odds in favor of winning against horse B or something like this. So if you kind of recall, if we have odds in this manner, so if we have odds like this, 2 to 3 odds in favor, remember that this 2 is the size of A, and 3 is the size of A complement. So we know that we have an A and we have an A complement. In other words, we have something that passes and we have something that fails. So this is the perfect way to use binomial distribution. So in this case, we know that horse A will win 2 and horse B will win 3 times on average, right? So we're going to look at the binomial distribution in terms of odds to kind of see what this kind of gives. And it turns out it gives us something super, super nice and actually helps with the binomial distribution. And let's actually look at an example. So say I look at the binomial distribution where I have P 1/2, so think of a coin flip. And I'm doing this 10 times. So I flip the coin 10 different times. So we have n equals to 10. Now I'm going to draw a histogram of this. So what you can kind of see is we end up with the following kind of distribution. So in other words, out of all the different possibilities, right? So we have 2 to the 10 different options. Roughly, it looks like about 250 of them will have 5 heads, right? So this is the number of heads. So it looks like almost none of them will have 0 heads. It looks like about 10 will have 1 head. About 50 will have 2 heads. About 125 will have 3 heads. Around 210 will have 4 heads. And around 250 will have 5 heads. And actually, I know exactly what this is. This is, so I'll write these down in black. We have 1, 10, 45, 120, 210, 252, and then we go back down. You can kind of see this is exactly identical on either side. 120, 45, 10, and 1. And this is really coming from the choice function. So each of these is really the choice function. So this is 10 choose 5. So you can calculate this 10 factorial, 5 factorial, 5 factorial, and you'll get 252. And so we have this nice distribution. And what we're going to do is, since we're looking at odds and comparing things, let's look at them comparatively. So if I look at 1 compared with 10, so if I divide kind of the two, I'll get 10 compared with 1, right? If I look at the next one, I'll have 45 over 10. Then I'll have 120 over 45. Then I'll have 210 over 120. 252 over 210. 210 over 252. 45 over 120, 10 over 45, and 1 over 10. So these are kind of the ratios between them. But the thing you'll notice is I can actually divide things out, right? So here I can divide out of 5. 5 over 5. Here I can divide, I think it's 15. 15. Etc. And what we end up getting here is we get 10 over 1. This comes down to 9 over 2. This becomes 8 over 3. This next one, it becomes 7 over 4. So I can remove 30 from either of them. And you can kind of see where this is going. So we get 6 over 5, 5 over 6, 4 over 7, 3 over 8, 2 over 9, 1 over 10. And it's actually not too hard to see this. So if we look at these little things, right? So if I have n choose k, right? We said this is what this was. And I divide n choose k minus 1, which is our ratio basically. What we end up having is, let's do this one at a time, n factorial, k factorial, n minus k factorial. Then I divide by, I'll make this bigger, n factorial, k minus 1 factorial, n minus k minus 1 factorial. So if I flip it and reverse it, let me actually move this a little to the left because I'll need more room. Oops, I don't need that much. I just need, oops, no. Undo this line. Oh, I know why this is doing this. Yeah, okay, let me bring this over. N factorial over k factorial n minus k factorial divided by n factorial k minus 1 factorial n minus k minus 1 factorial. Okay, cool. Now I can remove this part. We'll make this bigger so I can easily do this. Ta-da! Bye! Before I forget, let me make this smaller again. Okay, cool. So let's flip it and reverse it. So we have n factorial over k factorial n minus k factorial times k minus 1 factorial. So here I'll distribute this negative sign, n minus k plus 1 factorial over n factorial. These n factorials cancel. This k minus 1 will remove everything except for 1k. And this n minus k factorial will remove everything except for one of these. So this we get n minus k plus 1. And so we're left with n minus k plus 1 over k. And so we get a super nice formula for something that looked complicated before. This formula is literally what's happening here. And so what this basically allows us to do is it allows us to look at the binomial distribution in a much better light. So we can kind of see exactly how this expands for arbitrary things, right? Because we're not looking at just 1/2. We're looking at any arbitrary p. And this is known as the consecutive odds for the binomial distribution. So this is kind of the theorem. So if I have n independent events, then the odds of k successes relative to k minus 1 successes, this is given by, so if I write this down normally, we have k successes in n trials divided by p of k minus 1 successes in n trials. This is what we were doing above. Now this ratio, right, so I put it in a ratio with 1. This is equal to, so we have almost the same thing on top, except here we need to multiply by p. And on the bottom we have k times 1 minus p to 1. And here you'll notice that if p equal 1/2, this implies 1 minus p is equal to 1/2, and they cancel. This is why we didn't see it in the previous kind of example thing. So we'll end the video here, and we'll look at a more thorough, in-depth example in the next video.